Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we'll be reviewing carboxylic acids and their derivatives. More specifically, how to convert between the derivatives via nucleophilic acyl substitution reactions. Now, before you watch this video, I do suggest a couple other videos for some prerequisite knowledge. One of them is the carbonyl substitutions and additions one-slide guide. The other is the hydrolysis one-slide guide, and as usual, I always recommend reviewing the organic chemistry reactions problem-solving process. So let's get started. Let's discuss the features of the carboxylic acid derivative functional groups. We're going to start off with Z. Z is going to determine the identity of the carboxylic acid derivative, and Z is known as the leaving group. How basic the leaving group is determines how reactive the molecule is going to be in nucleophilic acyl substitution reactions, with weaker bases making better leaving groups. The Z group is always going to be substituted out in nucleophilic acyl substitutions and replaced with something else. To the left of this, we have the carbonyl carbon. As is the case with all carbonyls, the carbonyl carbon is electrophilic, and this is the site that is going to be attacked by a nucleophile. We also have the carbonyl oxygen as well as the carbonyl pi bond. We can treat these as regions of excess electron density with the lone pairs on the oxygen and the pi bond on the double bond. As such, they can also act as weak nucleophiles and bases, and both of those sites can initiate substitution reactions by attacking acids or electrophiles. A lot of times we do this to make the carbonyl carbon more electrophilic. The most important thing that you need to know about carboxylic acids and their derivatives is their order of reactivity in nucleophilic acyl substitution reactions. We have the acid chloride, the anhydride, the ester and carboxylic acid, and the amide. And from left to right, we have decreasing reactivity in these nucleophilic acyl substitution reactions. And this can be explained in a couple of ways. First, we have increasing basicity of the leaving group as we look from left to right. In organic chemistry, the general trend for reactions is that equilibrium is going to favor the side with the weaker molecules. So if basicity increases as we go from left to right in this representation, that means reactivity is going to decrease. If you aren't sure why basicity of the leaving group increases from left to right here, you may want to review the video on how to rank the relative strength of acids and bases. That's going to make this so much easier on you, as you won't have to just memorize this order. You can figure it out in any situation. The general idea, however, is that basicity decreases the further right you go on the periodic table and the further down you go. That's why chloride is such a weak base and such a good leaving group. For the anhydride, we also have to consider the stabilization of the leaving group from resonance, which explains why the carboxylate anion is also a good leaving group. Rather than look at leaving group ability, we can also look at how stable the carbonyl carbon is itself. In other words, the more positive the carbonyl carbon, the less stable the molecule is, and the more likely it is to react in a nucleophilic acyl substitution. How do we tell how positive the electrophilic carbonyl carbon is? Well, we can look at resonance and inductive effects. If we look at the acid chloride, chlorine is more electronegative than carbon, so it pulls electron density away from the carbon and towards the chlorine. That should make that carbonyl carbon more positive. We can also look at resonance effects. And when we're talking about resonance, we can say, how well does that chlorine donate electrons to the carbonyl carbon? There are 3 lone pairs on the chlorine, and we can draw a resonance structure by drawing these arrows. However, chlorine being lower on the periodic table than carbon is going to have a poor resonance donating effect because of inefficient p orbital overlap. So while it does technically have a resonance structure that we can draw, it's a very minor resonance structure, and we do not donate electron density very well to that carbonyl carbon. In other words, the electronegativity difference is the major factor, explaining why the acid chloride is so much more reactive than the other derivatives. If we look at the other side of the spectrum with the amide, While we do have an electron withdrawing effect due to electronegativity, differences between the nitrogen and the carbon, we also have a very strong electron donating effect due to resonance. That's because nitrogen is a very strong base, so it's going to donate electron density via resonance very well. So if we draw in the lone pair and show the resonance donating effect, what we end up getting is a resonance structure that is actually a very good contributor to the resonance hybrid because of how readily nitrogen is going to donate its electrons. Because of that, that carbonyl carbon is a lot less positive than it is in the acid chloride especially. Because it's less positive, it is less reactive. What is the practical takeaway? More reactive carboxylic acid derivatives can be converted to less reactive carboxylic acid derivatives readily. However, less reactive carboxylic acid derivatives cannot easily be converted to more reactive ones. In other words, we can turn the acid chloride into an anhydride ester carboxylic acid or amide. However, I cannot turn an anhydride into an acid chloride, or an ester into an anhydride, or an amide into an ester. The exception to this rule is the carboxylic acid itself, which can be made from and converted to any of the other carboxylic acid derivatives. With that being said, now we can get into all the reactions. In general, there are two types of nucleophilic acyl substitutions that we can do with these carboxylic acid derivatives. The first involves a negatively charged nucleophile, and the mechanism here is pretty simple. The lone pair on the negatively charged nucleophile is going to attack the electrophilic carbonyl carbon, and when that happens, that is going to send the pi bond up to the oxygen. That's going to give us this intermediate where we attach whatever that nucleophile was to that carbon. The lone pair that we just sent up to the oxygen will now come back down, and as a result, that is going to kick off our Z leaving group. That, of course, gives us our substitution product. The other reaction involves a neutral nucleophile. Here, the lone pair on the neutral nucleophile is still going to attack the electrophilic carbonyl carbon, and we're going to send that pi bond up to the oxygen, just like we did before. The second step is the same as well. The lone pair that we just sent up is going to come back down and kick off our Z leaving group. This time, however, we have a product that still has an extra hydrogen on it, giving us a positive charge, which we don't want. So we're going to need some base to come in and remove that hydrogen. Once the base removes the hydrogen, we have our final substitution product. Because acid chlorides are the most reactive of the carboxylic acid derivatives that we're going to look at, they can be converted into any of the other derivatives very easily. The mechanism for these reactions is going to be identical to what we saw on the previous slide. So let's convert this acid chloride into an anhydride by reacting it with a carboxylate anion. As we would expect, the lone pairs on this negatively charged oxygen are going to attack the electrophilic carbonyl carbon and send the bond up to the oxygen. After that, the lone pair is going to come back down and kick off the leaving group. That, of course, gives us our anhydride product. To create a carboxylic acid, the reaction mechanism is identical to the one above. In the first step, we attack the electrophilic carbonyl carbon and send that pi bond up to the oxygen. In the second step, it comes back down and kicks off the leaving group, giving us our final carboxylic acid product. Because acid chlorides are so reactive, we can use neutral nucleophiles to carry out these substitutions as well. In the top two examples, we're going to use a neutral oxygen nucleophile, and for the bottom example, we're going to use an amine as our neutral nucleophile. Remember that if we use a neutral nucleophile, we have to have some base to carry out a deprotonation step to give us our final substitution product. In the case of using the alcohol or water, we use pyridine to deprotonate. To make the amide, we actually just use a second equivalent of the amine itself. The reaction mechanism for all three of these reactions is, of course, going to be the same. with the lone pair on either the oxygen or the nitrogen attacking the electrophilic carbonyl carbon on the acid chloride. The second step, as you'd expect, involves the lone pair coming back down and kicking off the chloride leaving group. This gives us our protonated substitution products, which of course will be deprotonated by our base in the last step. And that's how you can make an ester, a carboxylic acid, or an amide using neutral nucleophiles. Anhydrides are slightly less reactive than acid chlorides, and as such, they can be converted to esters, carboxylic acids, and amides as well. In these reactions, we use neutral nucleophiles, and the mechanism is nearly identical to the mechanism we use to convert the acid chlorides. We'll highlight the differences. The first two steps in these reactions, of course, is exactly the same, where we attack the electrophilic carbonyl carbon on one of the sides of the anhydride and send the bond up, and in the second step, the lone pair comes back down and kicks off that OAC leaving group. OAC is, of course, just the abbreviation of the carboxylate leaving group. That gives us our protonated substitution products. Now here's where we diverge a little from the reaction involving the acid chloride starting material. With the anhydride, the leaving group was a carboxylate anion, so we actually do not need to use pyridine for these first two reactions, because the carboxylate itself will be able to serve as the base to deprotonate the intermediate. In the case of making the amide, however, we still need two equivalents of the amine, and that's because amines are more basic than the carboxylate anion, so in order for this reaction to go to completion, we're going to need to use two equivalents of the amine. After the deprotonation step for all of these, of course, we get our final substitution products. Notice that we get an additional carboxylic acid product in the first two reactions, and we have a carboxylate anion as one of the products in our final reaction. Esters are much less reactive than acid chlorides and anhydrides, and as such, they can only be readily converted to carboxylate anions, carboxylic acids, and amides. Let's take a look at the reaction that converts an ester into a carboxylate anion. To do this, we react the ester with OH-. As usual, the first two steps of the mechanism are identical to what we've seen so far. After we kick off the OR leaving group, however, we do have an OR- in our reaction solution. Because carboxylic acids are fairly acidic, that OR- will come in and do an acid-base reaction with the hydrogen, giving us a carboxylate anion and an alcohol. If we wanted to further convert the carboxylate into a carboxylic acid, we would have to have some acid to protonate at the end. Although it's a lot simpler and more efficient to create amides in other ways, it is possible to turn an ester into an amide as well. The first two steps of the reaction mechanism are exactly what you'd expect. So far, however, when we've created an amide, we've used two equivalents of the amine. However, in this reaction, we can simply use the OR- that left to deprotonate. You can see our final products are the amide and an alcohol. Next, let's talk about converting an ester to a carboxylic acid and its reverse reaction, converting the carboxylic acid back to an ester. Both of these are done with an acid catalyst. To convert the ester, we're going to rewrite our acid as HOH2 to more easily show the acid-base reaction. We're going to use either the lone pairs on the carbonyl oxygen or the pi bond itself as a base to attack that hydrogen in H3O+. Now, it really doesn't matter which one we use, the pi bond or the lone pair, because what you get in the intermediate is a resonance-stabilized cation. So either way you draw it, we're still going to be able to draw that resonance structure. What this should show you is that due to resonance, what we're effectively doing is making the electrophilic carbonyl carbon even more electrophilic. That's actually what allows the oxygen lone pairs on water, a weak nucleophile, to come in and attack that carbonyl carbon. After the water attacks the carbonyl carbon and we get our intermediate, the next four steps are going to convert this into a carboxylic acid. It's mostly just a series of proton transfer steps with a leaving group leaving in the middle. I'm going to show all those steps at the same time. Most classes will not require you to know the entire mechanism of this reaction. However, some might. So feel free to pause the video once all the steps are on the screen to really understand how this works. The entire mechanism may look overwhelming and like a lot of steps. However, what you need to keep in mind is at the end of the day, all we're doing is we're doing a substitution of an ester. We can recognize that by saying, what are we substituting out? That is the OR group. And when we use excess water and acid, what are we substituting in? An OH group. In fact, you may remember from previous videos that whenever we have H3O plus by itself on the line, we're really just doing a reaction called hydrolysis. And we can actually use the hydrolysis shortcut to get to the final answer for this without actually understanding or drawing the mechanism. Of course, it's a great idea to always understand mechanisms for your understanding of organic chemistry, but there is the hydrolysis shortcut that you can use. If you're unfamiliar with the hydrolysis shortcut, feel free to check out the one-slide guide video I have on hydrolysis. This hydrolysis reaction that converts an ester into a carboxylic acid is a reversible reaction. Hydrolysis is carried out in excess water. However, if we carry out the reaction in dehydrating conditions, or remove water as it's formed, we can turn a carboxylic acid back into an ester. All we need to do is react with an alcohol in acid. Sometimes, on the reaction arrow, we also include something like minus H2O to indicate that we're removing water as it's formed. This reaction is called Fischer esterification. The steps in this mechanism are nearly identical to the steps in the hydrolysis mechanism, except now we'll be kicking off an OH group instead of kicking off the OR group. You can now see the entire reaction mechanism. Once again, feel free to pause the video so you can make sure you understand each of the individual steps, which again consist of a lot of proton transfers and a leaving group leaving. Note the similarities between this reaction and the conversion of the ester into the carboxylic acid. We've just seen one reaction of the carboxylic acid. However, before we get into the other reactions of the carboxylic acid, it's important that we understand the functionality of the carboxylic acid group. They don't behave like the carboxylic acid derivatives, and that's because the most important thing about the carboxylic acid is that it is, in fact, an acid. And, compared to other organic acids, it's relatively strong. So we're going to look at the Z group on the carboxylic acid, that OH. It has an acidic hydrogen, and because of this, it is readily deprotonated by amines, alkoxide anions, and other bases that might be stronger than those. Because it's an acid, that means that the substitution reactions that we're capable of doing with the other derivatives are not likely going to be possible with the carboxylic acid, because a lot of nucleophiles can also act as bases. And acid-base reactions occur more quickly than reactions between nucleophiles and electrophiles. So although we do have an electrophilic carbonyl carbon, if we have something that's strong enough to attack there, it's likely also strong enough to do the acid-base reaction and simply deprotonate the carboxylic acid instead. We can also say that that OH group is a leaving group. Even though it has about the same ability to leave as the OR group on an ester, it's unlikely that it's actually going to leave in a normal way, again, because to do so, we'd have to do a normal nucleophilic acyl substitution reaction. So for the carboxylic acids, we say that they can do nucleophilic acyl substitutions, however, they can only do them under special conditions. We'll see several of these special conditions in the reactions that follow this slide, but in general, what we'll be doing is we'll be turning that OH into a better leaving group, or we'll be making the carboxylic acid a stronger electrophile by taking advantage of the nucleophilicity and basicity of that carbonyl oxygen and pi bond. As it was mentioned early on in the video, any of the carboxylic acid derivatives can be turned into a carboxylic acid, and a carboxylic acid can be converted to any of its derivatives as well. Let's take a look at the reaction that converts a carboxylic acid to an acid chloride. To do this, we're going to use the reagent SOCl2. And SOCl2 actually looks like this. The sulfur in SOCl2 is extremely electrophilic. So much so that this oxygen and pi bond area of excess electron density in the carbonyl is going to come up and attack the sulfur. This will send the pi bond up to the oxygen in the SOCl2. Now when this happens, we can also show the lone pair in this OH group coming over and forming a double bond. That's going to give us the following intermediate. In the next step, and this should look very familiar, the lone pair that we just sent up to that oxygen is going to come back down, reform the double bond, and kick off one of these chlorines. The intermediate that's formed is going to be deprotonated by the chloride anion. And if we rotate the product from this step, we're going to see something that resembles something very familiar. You can see here that this intermediate looks an awful lot like an anhydride, except this OSOCl is an even better leaving group than a chloride. What we've effectively done is we turned an OH group, which is not that great of a leaving group, and converted it into this OSOCl, which is an incredibly good leaving group. So now that we've done this, we can actually carry out a nucleophilic acyl substitution. We're going to take a chloride anion from somewhere in the reaction chamber, and this is going to come up and act as a nucleophile and attack this electrophilic carbonyl carbon, of course sending this bond up as we're very familiar with by this point. After that, of course, the lone pair is going to come back down from the oxygen and kick off the OSOCl leaving group. That gives us our acid chloride product and our OSOCl negative. Now that OSOCl negative will degrade and form SO2 and Cl negative, which explains why we had enough chloride anion in this reaction mixture. Converting a carboxylic acid to an anhydride is possible in certain situations as well. Acetic acid, for example, if we provide enough heat for this endothermic reaction, will react with another acetic acid molecule to create an anhydride. The mechanism is the same as other mechanisms involving neutral nucleophiles, so none of these steps should be anything that's surprising. This reaction isn't very practical, and there are other easier ways to make anhydrides, so while this mechanism does make logical sense, it's probably not that important that you know it, especially since not very many carboxylic acids can do this, as they'll degrade under the high heat. Dicarboxylic acids, on the other hand, can undergo intramolecular reactions to create cyclic anhydrides. The mechanism, of course, is very familiar. Feel free to pause the video if you want to review it. Even though the carbonyl carbon of a carboxylic acid is more electrophilic than the carbonyl carbon of an amide, we can't simply do a regular nucleophilic acyl substitution with a carboxylic acid reacting with an amine. That's because the amine is basic, and of course the carboxylic acid is acidic. So what's going to happen if we react an amine or ammonia with a carboxylic acid is we're simply going to do an acid-base reaction. That's going to give us an ammonium salt. What's interesting in the case with ammonia, however, is that if we heat this up to high temperatures, we're going to get a dehydration and create an amide. The mechanism for that reaction is beyond the scope of this video. So, and I rarely say this, just memorize this one. If you add NH3 with heat to a carboxylic acid, you will end up doing the acid-base reaction followed by a dehydration to get the amide. If we react a carboxylic acid with a primary or secondary amine, however, we simply cannot add heat to do a dehydration to get an amide product. All we're going to get is the deprotonation of the carboxylic acid. In order to prevent this, we need to use another reagent, something called DCC, to convert that OH into a different leaving group that isn't acidic. I've put an image of DCC below this reaction, that way you can get an idea of what it looks like, and also to show you why I don't really feel like drawing out the first couple steps of this mechanism. All you really need to know is that we turn that OH into something that I call ODCC. ODCC is no longer acidic, and it's a better leaving group than it was before, which makes it so that this nucleophilic acyl substitution is much easier to do than previously. The mechanism will now proceed as we would expect, with the nitrogen attacking the electrophilic carbonyl carbon. Once again, if you need to review this mechanism, feel free to pause the video, but it should look the same as all the other nucleophilic acyl substitutions at this point. Our final two reactions involve converting amides to carboxylates and carboxylic acids. Now normally, we wouldn't be able to go from something that is less reactive to something that is more reactive, but again with carboxylic acids, special things can occur. Don't get me wrong, these reactions are not easy to carry out. They involve very high temperatures, and they're incredibly slow. I won't give you a super in-depth explanation for why this can occur, but it involves a lot of probability and some logic. What you do need to know, however, is that these mechanisms are very similar to converting an ester into a carboxylate or carboxylic acid, and we can do them with either a base catalyst or an acid catalyst. In base, the first step of the reaction is exactly what you'd expect. The OH negative is going to attack the electrophilic carbonyl carbon, and one of the bonds in this double bond is going to go up to the oxygen. In the next step, the lone pair is going to come back down and kick off a leaving group. Now, OH is actually a better leaving group than NR2. And most of the time, we are actually going to kick off that OH. But like I mentioned, with probability, there is a very small chance that NR2 is going to get kicked off. That very low probability is why this reaction is so slow. So we're actually going to show us kicking off the NR2. That's going to give us a carboxylic acid and an NR2 negative. Now you may be wondering, can't that NR2 just go back and attack that electrophilic carbonyl carbon? And of course, the answer is no, because a carboxylic acid is an acid. And that means what's actually going to happen is that NR2 is going to deprotonate the carboxylic acid. This step is why this reaction is not reversible, because now we have a carboxylate anion and an amine. And once we have the carboxylate anion, which has a negative charge, we are not going to be able to attack that carbonyl carbon with the amine. Reacting an amide with H3O+ and heat is analogous to reacting an ester with H3O+. It's really just hydrolysis. And of course, we can use the hydrolysis shortcut that I discussed earlier and in a different video to get to the answer really quickly. Once again, I'm going to show you the entire mechanism, but I'm going to highlight specifically the differences at the end of this mechanism compared to the mechanism of hydrolysis of the ester. All of the steps I'm showing you right now are exactly what happens in the hydrolysis of an ester mechanism. In the last step shown on the bottom right, we are just kicking off that NR2H leaving group. Here's where things are slightly different. Because an amine is a lot more basic than water, in this next step, we're going to take that amine, and that is what we're going to use to deprotonate that positive OH. That effectively removes the basic amine from the reaction and explains why we don't get an additional deprotonation of the carboxylic acid. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.